Hello, my name is Matthew Lichtenberg, and today I'm going to be presenting my work on AI for nanoscale imaging of contact in the human-machine interface. I would like to thank the Invent Lab and the ORE program at Texas A&M University, without whom this project would not be possible, as well as Dr. Yuan Ma and Professor Cynthia Hipwell, whose mentorship was just as necessary. So as an overview, I'm going to go through the motivation for this project, then a little bit about the data processing and how we get and process our data, then the steps that we do to do machine learning, our results, some of the limitations of those results, then interpretations and further experimentation, as the interpretation of machine learning algorithms is notoriously difficult as they can behave like black boxes, and then finally our conclusions. The standard model of friction that's taught in high schools and even my mechanics courses in college has been the Coulomb model of friction, which, as it turns out, is just completely wrong. So this Coulomb model says that the frictional force is equal to a coefficient of friction, which is material dependent, times the normal force of the interaction between two objects. And this is just completely wrong because it assumes that contact area is proportional to the normal force, which is why the normal force is used, which just isn't the case. The Coulomb model predicts that for a block with the same weight, so the same normal force, and the same material, be it a block and tape, the maximum static frictional force is independent of the amount of contact between the surfaces, which, as anybody who has used double-sided tape will tell you, just isn't true. This implies that a block stuck to the surface with a square inch of double-sided tape has the same resistance to shear forces that a block taped with a square foot has. There are other models of frictional forces, such as the Hertzian model, which describes the frictional force as being proportional to shear stress as well as contact area. It does do a better job at explaining the physical phenomena that are going on with interfaces such as tape or human fingers. We're particularly interested in the case of human fingers, where the surface geometry is incredibly complex, and there are also a ton of potential applications, including the design of haptic surfaces. This brings us to the project goal, which is to answer the question of what is the true contact area of a finger on glass. And to do that, we need to explain some things. So here you can see what it looks like when we image a finger ridge, which are the microscale ridges on top of your fingerprints. We need to differentiate now between true and apparent contact. The dark spots are all contact of some form, but some of it we call true, whereas some of it is apparent. And that's because there's a lot of stuff on your skin. For example, we have skin oil or sebum, as well as sweat and water droplets and other oils and air pockets, and there are a lot of things that actually exist within this interface. Skin is really what matters for the purposes of friction, so we refer to that as true contact, and all of these other substances as false contact. But it's not immediately visible which is which just by looking at these images. We can see that true contact can generally be distinguished by two primary features. One is that it has a variety of wispy shapes, and they also tend to have significant gradients in their shading. Wet contact, or apparent contact, on the other hand, tends to take on rounder shapes because it's a liquid and it needs to maintain its surface tension. There also tends to be a more consistent coloration once you get past the boundary. However, for many points of contact, this classification is quite hard to make by the human eye, as contact spots can be somewhat round or somewhat shaded, or any combination of anything, really. This is where machine learning comes in. It would be very difficult to manually program all of the patterns that code for true or apparent contact. So what we do instead is give a computer a ton of examples with labels and have the computer figure out and learn the patterns on its own. In order to do that, though, first we need to do a little bit of data processing to get the data into a point where we can put it into the machine learning algorithm. The first thing that we do is remove the background because there are these dark spots on the glass that can interfere with our measurements and lots of other stuff. Also, there's the issue of background color, and different videos may have different background colors, and we don't want the algorithm to train and come up with results based on the background color of what it's trained on. So what we can do is remove the background with video processing using the first frame of each video segment. And while we're at it, we can also binarize the image and then also find the boundaries of those binarized images so that we can identify each point of contact within a given image. This is done by implementing two fairly standard algorithms, the first of which is the Bradley method, which allows us to binarize the image into just ones and zeros for each pixel value, and then the More neighborhood algorithm, which lets us trace out the boundaries of those new binarized images. We can then take the boundaries that we found and map them back to the original image, and then take the images in those boundaries and feed that into a machine learning algorithm. The benefit of processing our data like this is tremendous, particularly when it comes to the repeatability of the experiments. By putting all of the data into a standard form, we're able to reliably test and process that form using the same algorithms. The downside of doing all of this processing is that there is the potential for the loss of information, but as we'll discuss later, this may not actually be a bad thing. When it comes to machine learning and data labels, at first we're in a little bit of a bind. A machine learning algorithm needs data labels to identify images of fingers, but in order to create data labels, we need some way to easily or algorithmically assign labels to images of fingers, which is a bit of a catch-22 because if we had an algorithm to create the labels, then we wouldn't need a machine learning algorithm to do it in the first place. So the solution to this apparent paradox is to not start out with fingers at all. Instead, we're going to take our training images from gloved fingers. We can be sure that when we put on a dry glove and image it on the sensor that there's no skin oil, there's no water, and all of the apparent contact is going to be dry, true contact. This is different from when we have a wet glove, where when we image it, we'll get these big splotches of just water and contact and everything. But in the wake of that, we see water droplets, and we can isolate those water droplets and identify them and label them as images of water. With this method of acquiring images, we acquired over 8,000 images, a combination of wet and dry contact, about 60% dry. These images are then randomly split 80 to 20 between training and testing data. And then we send these training images through stochastic gradient descent in a machine learning architecture. The original architecture gave batch accuracy results in the high 90s, but then when it was run on testing data, it would perform in the mid 80s, which was an indication of overfitting. So after a couple of tweaks, this was the final architecture that I settled on. It's quite simpler, but it gets the job done and is capable of producing neural networks that achieve high 90s accuracy with the testing data. The bulk of the algorithm's complexity comes from two convolutional layers. As the initial training data and testing data is randomized, and additionally the training data is randomized after every epoch, we don't come out with one final accuracy, but instead a distribution of accuracies over 60 trial runs. The distribution was highly bimodal, which I think has to do with the high learning rate of the algorithm that was used. However, the algorithm did produce over 20 samples of very high-performing classification algorithms. Here you can see the results that come from applying the machine learning algorithm to every frame of a particular video showing a finger interacting with a surface. In red, we have the area of the total pixels of dark spots within each frame of the video, whereas in blue, we have what the algorithm perceives to be the true contact based on the training data. You can see in this next graph the same data expressed as a percent of the total screen, and there's very little actual contact going on between your finger and a surface. Most of it is air gaps in the ridges between your finger and the surface. But on top of that, most of that apparent contact is also not even true contact. We can take the ratio of total apparent contact to true contact for every frame of the video, and we can come up with this graph, which we can further condense into this histogram, which shows that on average, only about 46% of total contact area is actually true contact. We can also use this classification deep learning algorithm to identify which particular parts of each image are registering as true contact or apparent wet contact. There are several limitations and areas of development within these results. The most significant source of error is likely to be mixed contact. These are places where both skin and liquids are present, and the algorithm is only trained to classify these areas as one or the other, and they can't easily be distinguished or separated with image segmentation, and it would take quite a bit of effort and manual label assignment to crack this problem using further neural networks, so different techniques are likely to be needed. The algorithm is also trained based on a glove and not an actual finger, which may affect its performance. How similar is a glove to a finger is actually an open question. We're not entirely sure. This is more of an issue for the dry contact because water droplets on a glove should look similar to water droplets on a finger. One other potential source of error in this area is that the algorithm does not distinguish between sebum and water. Further, in an ideal world, we would test every one of these 60 neural networks that were created. However, this was not done for two reasons. One, because of hardware limitations, and all of this is running off of MATLAB on my laptop. And the second reason is that this isn't particularly practical from an engineering standpoint, in that we shouldn't spend significant resources training algorithms that are objectively inferior in their accuracy. Earlier, I had also mentioned the potential loss of information by removing the background. Anything that's brighter than the bright field of the image is basically ignored. However, this may actually be a good thing because we have reason to believe that lighter spots in many of these images are the indication of air pockets. And so by completely ignoring them, they're not even considered contact by any part of the algorithm, which is a good thing because they're not in any way contact. So with all that said, I wanted to get a better understanding of what is actually happening in the machine learning algorithm, because I've been looking at these images for about 2 months now, and I've been able to get a decent sense of being able to identify them by shading, color, and their shape. But I had a question: what is the largest identifying factor in terms of what the algorithm uses? So I came up with a hypothesis. If it's color distribution, then we should expect training on a grayscale version of the set of images to drop the accuracy substantially as compared to training on the color. Because if it can't see color, and color is the most important thing, then the accuracy will just plummet. Similarly, if shading or brightness is the most important identifying factor, then training on just binary black and white images will drop the accuracy substantially. But if shape is the largest identifying factor, then we can expect training on color, gray, and binary images all to have similar levels of accuracy. And so I ran the data on color images, gray images, and black and white images, and we found that while accuracy does decrease slightly as you decrease the amount of information you give to the algorithm, just training on images that have a pixel value of black or white gives nearly a 94% accuracy rating, which is really high considering it's just looking at black and white pixels. So from this we can conclude that most of the information has nothing to do with the shading or the color, but is stored solely in that shape of the contact boundary. Particularly, I imagine this goes back to what I was saying earlier about how liquids tend to form more rounded shapes because of surface tension. We can then plot these different algorithms and how they perform, and from there we can figure out what their differences are in how they perceive the real contact versus apparent contact. And it turns out that they do have statistically significant differences at the 95% confidence level in terms of what they consider to be true and apparent contact. In particular, the less information the algorithm is given, the more likely it is to identify a spot as apparent contact or wet contact. We can look for days in differences where one algorithm says a spot is one thing, whereas another says it's another thing, but we can see some general overall trends, and that is, as the algorithm takes in images with less information, it tends to take these more mixed areas of contact, or at least ones that we humans can see are mixed areas of contact, and prescribe to them the label of apparent contact for one reason or another. This is likely because we perceive there to be mixed contact because of differences of shading in these images, which the binary algorithm doesn't pay attention to at all. So in conclusion, true contact is important for understanding haptic interfaces. Most apparent contact is not true contact, and most contact can be identified as true or false by its boundary. Thank you for your time. Have a nice day.